So in this problem, we have a gas at a pressure of 699 millimeters mercury at 40 degrees Celsius. What is the temperature at standard pressure? First thing we need to do is identify the law that we're dealing with. We notice that we have pressure and we have degrees Celsius. Pressure and temperature combine to form Gay-Lussac's law. So Gay-Lussac's law Gay-Lussac's law tells us that an increase in temperature equals an increase in pressure. We could show it in a graph as temperature being the dependent variable, temperature being the independent variable, pressure being the dependent variable, and as temperature goes up, pressure increases. And so in our problem here, before we begin to do any math, our gas has a pressure of 699 millimeters mercury at 40 degrees Celsius. What is the temperature at standard pressure? Standard pressure, remember any gas at STP, standard pressure would represent standard pressure equals 1 atmosphere of pressure. It's always true. If it was asking a gas at STP, remember that STP stands for standard temperature and pressure. Standard temperature for a gas is 273 degrees Kelvin. And so we can make the assumption that this gas is in 1 atmosphere since it tells us that it's at standard pressure. Now, the formula for Gay-Lussac's law, P1 over T1 is equal to P2 over T2. In our problem, since we're calculating the final temperature, we need to convert this millimeters mercury into atmosphere. The conversion for that is that P1 is equal to 699 millimeters mercury divided by 760 millimeters mercury in 1 atmosphere. So 699 divided by 760 gives you 0.92 atmospheres. And so 0.92 is going to represent our P1. I'm going to erase this so we have some more room. 0.92 atmospheres is P1. So let's set up our equation. We have 0.92 atmospheres divided by our temperature. Our first temperature is at 40 degrees Celsius, so add 273 to convert it to Kelvin, and it'll be 313 Kelvin. Our gas is at STP, so we're going to use standard pressure. We're just at standard pressure, so we're going to use 1.00 atmospheres divided by T2. Now let's rearrange this equation to make sense of it. We have 0.92 atmospheres times T2 is equal to 313 Kelvin times 1.00 atmospheres. All I did was cross multiply the numerator from one side by the denominator of another. And so now we can solve for the right side of this equation. It's 0.92 atm times T2 is equal to 313 Kelvin times 1 atmosphere, so 313 Kelvin atmospheres. Divide both sides by 0.92 atmospheres. Cancel it out on that side. Divide by 0.92 atmospheres. We can cancel our units here. We're left with Kelvin, which is the unit we want to be in with degrees Celsius. When we divide these two numbers, you should get 340. T2 is equal to 340 Kelvin. And to see how that compares to our initial temperature, that was at 40 degrees Celsius. Let's convert this back into degrees Celsius. So remember, to go to degrees Celsius, we just subtract 273 from it. So T2 is equal to 67 degrees Celsius. That would be our final answer. So let's look at this 67 degrees Celsius and compare it to our initial temperature. We finished with 67 degrees Celsius. We started at 40 degrees Celsius, and we would expect, since we had an increase in pressure from 0.92 to 1 atmosphere, that the temperature should have gone up to cause that pressure to change. And so our answer does make sense. I hope this helps.